In this video we discuss section 18 onwards. In section 18 we need to discuss rings and fields. Rings and fields. These are algebraic structures, likewise group. The only difference is we start with a non-empty set R. In rings there will be two binary operations, say plus and multiplication. So the first binary operation is what we call addition. This is not usual addition. This is just the name for the first binary operation. And for the second binary operation, we use the word multiplication. Instead of saying second binary operation, we use multiplication. So these are two keywords in ring theory, addition and multiplication. Addition stands for the first binary operation of the ring, and multiplication stands for the second binary operation of the ring. The first binary operation is denoted by a plus symbol, and the second binary operation is dot. Now, in order to get ring structure, we start with a non-empty set R together with these two binary operations, and we need to observe that R under addition is an abelian group. This should be an abelian group, and if you say this is an abelian group, then we already assumed five binary operation, five axioms. First one is this addition is a binary operation, and second one is associativity of this addition. Then third one is the existence of identity. Fourth one is the existence of inverses for each of these elements of R, and finally the commutativity property. So all these five axioms can be abbreviated as abelian group. R plus is an abelian group, and if you observe the other binary operation, say multiplication, this should be a semi-group. Okay, this should be a semi-group. So in order to get the group structure, we start with non-abelian, non-empty set, and first with respect to first binary operation, this is an abelian group. With respect to second binary operation, this is a semi-group, and we will have two distributive properties. Distributive property of multiplication over addition. So if you choose any three elements A, B, C from the ring, then A times B plus C will give AB plus AC. This is what we call left distributive law, and similarly A plus B times C equal to AC plus BC. This is denoted. This is nothing but the right distributive property. So this is the distribution of multiplication over addition from the left, and the second one is the distribution of multiplication over addition from the right hand side. So if one structure has this much properties, then we can call this as ring. Okay. So likewise group, we define another structure, algebraic structure, what we call ring. Okay, so this is the definition of the ring. In this section, we will discuss the properties and examples of rings. Obviously, there are so many examples are there. First one is integers under addition, usual addition, multiplication. This is a ring. And the second is R under addition, real numbers under addition, usual multiplication. And third one is Zn under addition modulo n, multiplication modulo n. So this is an example of a finite ring. The later one is a infinite ring, R under addition, multiplication. And we have another example, set of all m by n matrices, okay, which is denoted by m and R. This is a set of all m by n matrices over R, usual matrix addition and matrix multiplication. So this will give a ring. And there are so many other rings are there. Some interesting rings are, if you consider set of all functions, we call R as set of all f from real numbers to real numbers. So these are functions from R to R. We consider this is the set. Then in this set we define addition and multiplication in such a way that f plus g is defined. This is a function is defined by f plus g of x equal to f of x plus g of x. and f times g. This is the second binary operation of x equal to f of x into g of x. As these f of x and g of x are real numbers, the usual multiplication is there. Using this usual multiplication, we define multiplication of two functions. So this will give a ring structure. So there are so many other examples are there. For instance, if you have any two rings, then Cartesian product of rings is again a ring. Likewise, the Cartesian product of groups is a group. And next we discuss some symbol theorem, but this is very interesting theorem. 18.8 theorem. This theorem states that some property of the additive identity in a ring. Okay. So we start with a ring. If R is a ring, an orbit ring, then obviously the additive identity is denoted by 0. Okay. With identity, with additive identity as 0, then we have some properties. The first one is we know that 0 plus any element, say a times 0, this will give a times 0 itself, because a times 0 is an element of ring. Then 0 plus a times 0 is again an element of the ring, so that will give the same thing. But we know that a times 0 can be replaced as a plus 0 plus 0, because 0 plus 0 is 0 itself. Using the left distributive law, this is a times 0 plus a times 0. As under addition this is a group, you can by using right cancellation law, you will get 0 can be written as a times 0. Okay. In the similar fashion, you can prove 0 times a is also 0. So in a ring, if you multiply additive identity with any other element of the ring, which yield this 0 itself, okay, additive identity itself. This is the first fact. And the second statement is a times minus b. This is in fact minus ab. This is also same as minus a times b. What does it mean? The additive inverse of ab is a times minus b. So if you operate a times minus b with ab, by using the left distributive law, you will get this is a plus a times b plus minus b, that is a times 0, which is equal to 0, which shows that when you operate ab with other element a times minus b, you will get 0. That means what is the inverse of additive inverse of ab? That is nothing but this element. So this proves the first equality. The similar fashion, you can easily prove that minus a times b, when you operate this with ab again. Okay. So using right distributive law, this is minus a times minus a plus a times b. This is 0 times b, obviously that is 0. From this you can say that minus a times b is also additive inverse of ab. But we know that additive inverse of ab is unique in a group. Therefore you can write this minus ab simultaneously equal to a times minus b and minus a times b. So this proves the second statement of the theorem. Using the second statement, you can easily prove the third statement. What is the third statement? When you operate minus a with minus b, okay, if you observe this thing, minus a times minus b equal to minus ab, right? So instead of taking a, we collect minus a here, and instead of minus b, we have minus b. Okay, then you just apply this thing. Okay. So what is the left hand side? Instead of a, we have to write this is minus of. Instead of a, we have to write minus a, and instead of a is a itself. So I write it as this form. This is same as minus of a times minus b. Okay, so that is when you collect, when you consider this element minus, so by substituting we consider this one, I will put it in the bracket here. You just observe the previous result with the first equality, A times minus B. Okay, so if you put or if you replace A by minus A, you will get this one. If you replace this A as minus A, then you will get this thing. When you replace this B by minus B, if you replace B by minus B, okay, then you will get right hand side. Okay, now this is also equal to what do you write? Minus A times. Okay. So we consider these two things, minus of AB equal to minus A times B. In this equation you put B is equal to minus B, so we put B is equal to minus B here. Then what is the conclusion? Left hand side will be this one, minus of A is same as A and B is replaced by minus B. Okay, and what is the how will we get this LHS? By replacing this B by minus B. So since these two quantities are equal for every A and B, you can just replace B by minus B, then you will get this one. Okay, so finally minus of, you just apply the result again, A into minus B, that is minus AB, so that is minus AB, that is equal to minus of minus, additive inverse of AB, that is AB itself. So this proves the third condition. So this is the interesting theorem, the very beginning of the section 18. Next we will discuss what is the implication of the concept of homomorphism when we move on to ring from the group. So this is in this 18.9 we can see the definition of ring homomorphism. In ring homomorphism, we define a function from a ring R to another ring R prime, same as the group, and we collect two conditions, phi of A plus B equal to phi of A plus phi of B. Not only this, we need to check one more condition, as this ring contains two binary operations. So this phi preserves the first binary operation. Preserves means phi satisfies the first condition, and similarly phi should satisfy the second condition as well. So phi of AB is equal to phi of A, phi of B. If these two conditions are true for any A comma B belongs to R, then we can say that phi is a ring homomorphism. Okay, ring homomorphism. So in order to get a ring homomorphism, you first verify whether that is a group homomorphism, because R under addition is a group. In fact, it's an abelian group. So we need to consider a function from R to R prime that should satisfy the condition of a group homomorphism, as this R plus underlying group is there. Okay, abelian group is there. So the number of ring homomorphism is always less than number of group homomorphism, because we verify a homomorphism is a ring homomorphism by verifying first that that is a group homomorphism. Okay, so this is because there are homomorphisms. Say if you consider Z under addition, multiplication, and we have another ring as same as Z, addition, multiplication. You consider a function phi, okay, phi from this ring to the same ring, defined by phi of n is equal to 3n. Okay, this is true for every n belongs to Z. Obviously, this is a ring homomorphism. That means this satisfies the first condition of the homomorphism, that is phi of n1 plus n2 equal to 3 times n1 plus n2, that is 3 times n1 plus 3 times n2, that is equal to phi of n1 equal to plus phi of n2. So this always satisfies the first condition. So we can consider the Z underlying group Z plus, then phi can be considered as a group homomorphism from Z plus to Z plus. But the fact is, if you consider the second condition, what is phi of n1 n2? This is in fact 3 times n1 n2. But what is phi of n1 times phi of n2? This is in fact 3 times n1 into 3 times n2 as well. So that is 9 times n1 n2. This need not be same as the previous one. So from these two observation, you can say that n1 n2, phi of n1 n2 need not be, or in general phi of n1 into phi of n2. Okay, so need not be, this is not equal. So which shows that phi is not a ring homomorphism. In fact, this phi is a group homomorphism. So this is the difference between group homomorphism and ring homomorphism. So there are so many homomorphism can be defined from one ring to another one. For instance, we can consider for R and R prime or any arbitrary rings, then you can define phi of n, phi of any element R equal to 0 for every R. This is a trivial homomorphism because phi of R1 plus R2 is equal to 0, phi of R1 equal to 0, phi of everything is mapped to 0. So we have this one. So phi of R1 plus R2 is equal to this one. Similarly, phi of R1, R2, that is also 0. Then this is vacuously true. That means this phi is for any arbitrary, any two arbitrary rings, there is at least one ring homomorphism from a ring to another ring. Okay. Now we can think of multiplicative questions. That is whether what are the properties of the multiplications of a ring. Now we address the multiplicative questions. That means if you recall the definition of a ring, R under addition multiplication, we can think of R plus is an abelian group, and R multiplication is a semigroup, So what do you mean by semigroup? Semigroup means it should satisfy, or this is a binary operation anyway. Multiplication is a binary operation, and that star is, this dot is associative. Okay, this is the only axiom. This operation multiplication is associative. Now we can think of this corresponding to this associative binary operation. There should exist a identity. Okay, identity corresponding to this this multiplication. That is second binary operation. If there exists an element, what is the identity of identity corresponding to second binary operation? If you choose any a from ring and multiply it with 1, that is equal to 1 times a, that is equal to a for every a. If there exists such an element 1 in that ring, if this 1 is an element of the ring R, then we can say that 1 is the unity. Unity means multiplicative identity. So once a ring has this multiplicative identity, then you can say that that ring is a ring with the unity. So interesting fact is, if we start with a ring with unity, and it is abbreviated as RU, if we start with a ring with unity, then you can easily define a homomorphism. So phi from R to R prime, okay, R prime. Then suppose R is a ring with unity, R is RU, ring with unity, then obviously that should contain 1. Okay. Now you define phi of any element, okay, or phi of 1 is some element of R, some element R prime of R prime. Then you can get, you define using this argument, you define phi of x. Okay, what is phi of x? Phi of x is, or phi of R. Okay, you can write phi of R. Phi of R is defined as R times phi of R. Okay, R times phi of n. Then this is always a homomorphism, because phi of R1 plus R2 that is equal to what is that one, R1 plus R2 times phi of 1, that is R1 times phi of 1 plus R2 times phi of 1. So this shows that this is phi of R1 plus phi of R2. Okay. Now you write phi of R1 R2. Okay. So this is what does it mean? Phi of R times phi of 1 means if you operate phi of 1 R1 times, that is the meaning of this thing. Okay. So this is R1 R2 times 1. Okay. What is the meaning of R1 R2 times 1? R1 R2 times 1 means R1 times, if you operate 1, R1 times first, R1 times, then operate R2 times. Operate R1 R2 times. Then you can say that R1 R2 times 1 is equal to R1 times 1 into R2 times 1. That is phi of R1 into phi of R. So R times phi of R equal to R times 1 is always a homomorphism. Okay. So this is an example of a homomorphism. In fact, this is an example from since this R1, R2 are numbers. I assume that these are numbers. Then this R can be considered as an element of a ring Z. Okay. Then you can easily define this homomorphism as a consequence of the existence of unity. Now, if this R, for a ring we have, this is an abelian group. Again, we recall that, and R is semigroup. If this semigroup is commutative, okay, that means any R1, R2, we have R1, R2 is equal to R2, R1. If this happens in a ring, then we can say that that ring is a commutative ring. Okay. This is the definition of commutative ring. So commutative ring is nothing but a ring in which multiplication is commutative. Okay. Suppose a ring has a commutative ring and it contains unity, then that ring is called commutative ring with unity. Okay. So this is the abbreviation for commutative ring with unity. So if you write commutative ring with unity, then we can this much axioms. That is, first one is R is a ring, obviously. R under addition is a abelian group, and R under multiplication is a abelian monoid. Okay, abelian monoid. Monoid means it has identity. Need not this monoid need not contain the inverse elements for each of its elements. So abelian. This is not AB. Abelian monoid and abelian group. Okay. So this is the definition of a commutative ring with unity. Now, before thinking of the commutativity of the multiplication, you can think of the inverse of existence of inverse in a ring. Okay. Suppose we have a ring R under addition. Assume that every non-zero element in R has multiplicative identity, multiplicative inverse. In order to speak about the multiplicative inverse, we need to speak about the multiplicative identity. So if you start with a ring and if we address the question every non-zero element has multiplicative inverse, then we should start with ring with unity. Okay. So because that ring should contain identity, then only we can speak about the inverse of an element. So every non-zero element in a ring which is a ring with unity has multiplicative inverse. This is the question we have to address. If such question is positively true, or the answer is if we answer this question positively, then you can call this R. Okay, this ring is such a ring is called skew field. skew field or division ring. So what is the definition of division ring or skew field? Okay. Division ring means, or skew field means, that is a ring with unity. Ring with unity, R is a ring with unity, and R under addition is an abelian group, obviously abelian group, and R, if you consider only non-zero elements, so R minus 0, we avoid that 0, and under multiplication is again a group, so that should not be a commutative group. So we address only the question of existence of the inverses. So if this happens, then every division ring can be considered as obviously, since this is a division ring, then it satisfies all the other axioms of the ring. Okay, along with that, this should be, this R minus 0 under multiplication is a group. Okay, such a structure is called skew field. So if you assume commutativity also in a skew field, okay, that means commutative skew field. Okay, if you start, if you consider commutative skew field, then that structure is what we call field. Okay, so this is the definition of field. The field is a commutative skew field. Commutative skew field is a ring with unity, with all the non-zero element has every non-zero element has its own multiplicative inverse. A number of examples are also discussed in that one. So along with that, we can conclude section 18.